Hi, everyone, and thank you for joining us today. My name is Victoria. I am Employer Brand and Event Specialist at Intellias. While we are waiting for some participants, I'd like to tell you a few words about our company. Intellias is a global technology company with over 3,200 specialists on board. We combine engineering, craftsmanship, and technology expertise to solve challenges of any nature, scale, and complexity. Our development centers are located in Poland, Croatia, Bulgaria, Ukraine, Spain, Portugal, Colombia, and India. We also have representative offices in Germany, the USA, the UK, and the United Arab Emirates. A few organizational moments. Firstly, you can put your questions to a speaker here in YouTube chat. I'll read them and Sergii will answer after the presentation. One more thing, we'll send you email with the webinar recording, speaker's presentation, and feedback form tomorrow. We highly appreciate your feedback and it helps us to improve our future events. So let me introduce Sergii Zubovych, Senior Scala Engineer at Intellias. Sergii, please go ahead.
Okay, so hello, all of you that behind the screen. And today we are gonna talk about Scala collections, quite complex topic. And we're gonna talk about more conceptual things. Conceptual things that will allow us to understand what are Scala collections essentially. So before that, a few words about myself. So my name is Sergii Zubovych. I'm a senior Scala developer in Intellias. So for the last 7 years, I'm with Intellias. So I've been working on primarily with location-based services and especially on creating maps. So creating maps and the things that related to it. So algorithms, data structures. So and data structures and algorithms are the part of my daily work. Before the Intellias also have experience in different domains except location-based services. So I had experience with financial services and as well as gaming, gambling, and betting. So basically that's it. I'm mostly interested nowadays. I'm mostly interested in algorithms, data structures. As I said, I work with them on my daily basis. So today's agenda. So actually, we start from the small recap of data structures. So we just look at like typical data structures to refresh our memories because I think many of you know what are data structures and what kind of data structures there are in the world, but for the sake of like coherency, we will do that small recap. Then we focus on abstract data types. It's also important computer science concept in the sense of Scala collections. They will be helpful for us, and we'll see it in a little bit later. And then we'll talk about Scala collections, how they are organized in general, how they build, from the point of view data structures and abstract data types. And then we will go to deciding factors. So the part of our daily work, if we'll try to use some collections for our application, we'll need to understand what to choose. And we'll focus on requirements and design factors that that it is worth to pay attention. And the final step will be asymptotic notations. So that is notation which is understanding which is important to understand performance characteristics of any Scala collection. Okay. So programming is understanding. To do anything with our code, we need to understand what we are going to do, what we are dealing with, and we need to understand any collections that we deal with. What is it? What behind that? How we can use it? So we need to ask that questions, and we should have answers for them. So what is data structure? Yeah, basically, it has three main components in it, three main ideas. It's a collection of something. Yeah, usually it could be like collection of some typical things, like which is ordered like a list, or some associations between some object and another object. So typically we see a data structure like a collection of some data, of some type of data. Data structure also have this notion of relationships between these objects, like associations between the elements. And data structure provides operations. Operations, that is basically the most useful part of it. So we use operations for something, we search data structure elements, we modify, we update. We do a lot of stuff without operations. So a few examples. Here we see like typical. I wouldn't say not typical, but I picked that list of data structures deliberately. They are all used in Scala collections. So array linked list. I think most of you are familiar with that the structures, as well as hash table. I guess I think a lot of heard about some kind of red black tree, but there are also interesting data structures like arrayed balance tree, hash arrayed mapped tree, so binary heap, which are also used in Scala collections. So they are behind the implementations, and so we need to understand them a little bit, understand like what they are and their performance characteristics. Another important concept when we talk about data structures is abstract data types. So basically, that is a concept of computer science, which is needed for the abstraction. So as data structure, it's kind of abstract thing by itself, but we also need to we can notice that many data structures have like something similar. They have similar operation, they have similar data properties, and abstract data types is a mechanism of grouping them and classify data structures. So for example, we can see that like list-like abstract data type fulfills to, for example, to linked list could be treated like a list-like data structure array could be treated like list-like data structures. So they're similar, and so they're similar in the sense that it's a ordered sequence of elements. We can address the elements inside the list. We can take, for example, head, tail, whatever. They have a similar interface. So when we talk about abstract data types, primarily we talk about semantics and about interfaces. And we will see like operating by this concept will help us in the task of like choosing and browsing the Scala collections hierarchy. So as I said, abstract data types is a mechanism of abstractions. We have a lot of data structures, but we have way more abstract data types. So if we need like navigate this domain of data structures, we can start from abstract data types and go deeper. So let's have a look. How does it work? So for example, as I said before, list abstract data type could be mapped to array or linked list. And for example, Q data abstract data type could be implemented in the means of array, linked list, or for example, circular buffer. We have another examples. For example, map could be implemented like hash table, or it could be implemented like a red-black tree, or hashed array mapped tree when it is immutable map. So we see how it works in practice. So having that two basic concepts, data structures and abstract data types, we can like deconstruct a Scala collection library and like see that general structure and understand why it's built like it's built, why we have that like hierarchy. Yes, and so basically, when we map a Scala collection library on these two concepts, we can see that, for example, we can see that the same abstract data type, which is list, yeah, could have a different implementations, actually, different implementations. For example, array sequence, array buffer, string builder. These are different Scala types and different Scala collections. And that different Scala collections actually use the same data structure behind it. And they fulfill the same abstract data type. And for example, if you look at the map abstract data type, as well, we can see that, for example, hash table as well have on the crossing of these two concepts, we have different implementations which are suitable for different different requirements and applications. So we have a mutable hash map. We have as well as mutable linked hash map and vector map. So we have different implementations. And knowing the data structure behind it, will actually help us to understand which one to choose. Yeah. And a few words about this mutability and immutability. So Scala collections are organized in that actually two packages. One package contains immutable collections and another contains mutable collections. And basically, mutable and immutable collections are based on the correspondent mutable and immutable data structures. And so, and knowing that data structure behind as well can help us to understand which collection to choose, which implementation to choose. So let's see on the, let's have a quick look on a hierarchy of immutable collections. We see that I took that like picture from the Scala standard documentation. And you'll see that like bluish rectangles, that's actually abstract types. Actually abstract types, interfaces, traits, like we could also can say that is traits. So we have on the top of the most generic abstract type, and we have below like different kinds, types and subtypes. Yeah. And we have that gray rectangles, which is actual implementations, so concrete implementations. And every concrete implementations have some data structure or just a few behind it. The same we can talk about mutable collections. So because we have a different set of mutable data structures, we will see that this hierarchy a little bit different because use cases for mutable data structures are also different. And we see the same structure, abstract types and concrete implementations. So having that understanding what are Scala collections essentially, having that two different views, like abstract data types and data structures. Then to pick something, to pick some concrete collection, we first need to understand our application requirements. Yeah, we should think about like what the properties of data we work with. Are they ordered, unordered? And do we need uniqueness? What the most frequent operations like we call? What actual operations do we need? What performance which we try to achieve? Do we need parallelizable code? Do we need a straight safety? And as well as another requirements, like can we use, for example, mutable collections, or like architecture and design of our application is immutable. We decided to do it immutable, and we don't want to use mutable collections at all. It's also could be a deciding factor. Should we like easy to change our code. So are we going to scale in our code? So there are many questions, so which is hard like to think upfront about, but anyway, before doing something, to write anything, we need to think about our requirements, and don't forget about to overthinking. Don't forget about the simple rule that we don't need over like complex systems. So the systems should be as complex as it can to solve this task, to solve the task that it is built for. So it pays a lot because our complex systems, they are hard to change, they're hard to maintain, they're hard to understand. So we pay a lot more for the complex system. If it don't force it and don't do it. So choose the most simple solution that works. So now we're going to stop a lot on asymptotic notation. This notation is important for understanding performance characteristics of data structure operations, as well as performance characteristics in terms of not only runtime of operation, but in terms of memory, in the case when it is important. So that is basically mathematical notation, and which was in mathematics before. It was introduced to computer science by very well-known Donald Knuth, a computer scientist. So basically, that person, I believe, started that discipline of algorithm analysis. So he first proposed to introduce that notation into the analysis of algorithms. And basically, idea behind that notation is to get rid of some details, yeah, and concentrate on more abstract things when we try to analyze algorithms and we try to compare algorithms. So we could pay attention to different aspects of our problem. For example, we could pay attention to the worst case scenario, to the best case scenario, or we're interested to some behavior that equal to some function. So in case we possibly we don't have the best case and worst case, we just have a single constant scenario which is not deviates a lot, and basically we can also be interested that something that is below some function, we don't know exactly what it is, but we are sure that it is that like ceiling is not reachable. So we have like three mathematical notation for it: big O, big omega, little o, and big theta. Big O notation used the most frequently. It represents the worst case scenario, and formally and pictorially, we could describe it like this. We have some function T of n. We might even like don't know what actually the function is. It could be runtime of our operation of our algorithm. And we have another function, f of n. If we can choose some constant n starting from that constant and some another constant c in such a way that we multiply c by fn, we always see that picture. So our function t of n is always below that upper bound. So in that case, we call that t of n is a big O of f of n. So it's upper bounded by some another function. Analogously, we can define in the same similar way the best case scenario, big omega. So the same function, t of n, f of n, the same constants, but we do vice versa. We say that we can find such a constants that our function t of n would be like bounded below of t of n. And in that case, we say that t of n is a big omega of fn. And theta notation combines both. So pictorially, we can see that it's kind of, there exist two constants, and we can say that t of n is big theta of fn, when we can find the two constants, and our functions would be the same time bounded above and below. So our functions will be sandwiched between the two functions. In the case of little notations, that it's more similar to big O notation, but more strict. We can say that for we can find some a constant n0, but for all constant c, our function will be bounded by that function of n. So that's basically mathematical and pictorial definition, yeah, of the notations. So if you look at Scala Collections documentation with on the page of performance characteristics and on the table, we can see how we can use it. So basically, we have different data structure here, and we have some typical operations, yeah, that we have in Scala Collections, like head, tail, apply, which could have different semantics in update, prepend into the beginning, and appending or adding to some data structure, inserting, removing, yeah. And we see that in terms of big O, there are data structure that quite fast. For example, of getting ahead. So it is very fast to get head of array, linked list, or for example, binary heap. Some operation like tail doesn't make sense, for example, for the array. But for the linked list, it's very fast, so it's constant time. So constant time means that it doesn't depend on the size of the collection. So it takes some time. Abstractly, we understand it's some time. In practice, that would be some number. And we'll talk about that constant factors, which is very interesting topic in regard of big O notation and analysis of algorithms. So we see here different functions. Yeah, we see here different functions, different big O's. And basically, having that, we can now understand that, for example, taking a head of a linked list is faster than taking a head of radix balanced tree. Yeah. By the way, that radix balanced tree is behind the vector that collection. So as said in documentation, vector have that effectively constant time. So, but mathematically, the time is logarithmic, but because the height of the tree is very low, so I have a little number of levels in the tree. You can say that it's effectively constant, but so mathematically, it's not true. Okay, let's have a look. Like it works, its practice. We will run and see. Of course, we won't run. I already run it, and we will see the results. Some very basic algorithms, like linear search on a linked list, linear search on the array, and binary search on the array. So I'm not going to stop on the implementation details. I think that they are very, very, very simple. And except binary search, I want to notice that is logarithmic, and it works when the array is sorted. So we go and divide our array every iteration we divide array by 2. We can add the element in the middle, and we see if the element in the middle is equal to our element that we're trying to look for, we just return. If it's less, we go left. If it's bigger, we go right. So every time we divide, we reduce the input size by 2. And that is why we have that logarithmic big O. So it's bounded by that logarithmic function of input data, of the size of input data. So I run 3 benchmarks, on the input, on different input sizes, and see that the maximal input size was 2 millions of entries. And we'll see that we have different times. Yeah. If we compare list search and array linear search, we'll see that they kind of look similar. Yeah, but list search is slower. List search is slower, a few times slower. And that's because constant factors. So the big O notation is quite abstract. we can reason about algorithm abstractly, but in practice, we have that constant C in that constant C have concrete value. So it depends on many factors. It depends on version of Java virtual machine, compiler, whatever. We have a lot of hardware. We have a lot of that stuff in real life, and that all influence. And we say that just a list and array have that different constant factors, and they have different running time. And so we see that array outperforms list. And that's because the modern hardware is built in the way that is more suitable for array-based data structures. And that is the explanation. And we'll see that, for example, binary search is like the zero. And it's not actually the zero, it's just much, much faster than linear search. And of course, to apply binary search, we need sorted array. So one important thing when we talk about big O notation, so when we try to compare two similar data structure that have like similar performance characteristic, we should pay attention to this constant factors in practice and measure it. Another more complex example, which is Quicksort. Basically, which is example of like fast algorithm, which is sublinear time, and actually n log n time, and it works. Our implementation works with array data structure, and our implementation is not optimal. There are more optimal way to implement, but that is for reason. It is not optimal in the sense of choosing that partition element, and we'll see how it influences the performance. So we have like two benchmarks of the same quicksort algorithm. One is which is quicksort. So we have that worst case of quicksort algorithm when the array is already sorted. So we don't progress on each iteration, and the running time is quadratic. Comparing to the regular case, which is in average sublinear and log n time. We have seen that again that that quadratic time is very, very slow comparing to that sublinear time. And talking about low order terms. So which is that? When we look at the code, we have that copy array function. Before we're doing that for like to make our sort function like pure. It takes some input, don't modify it, and produces new input. If we compare that copy array, we can see that we can neglect it actually. So it's neglectable. So when we compare the algorithms, that's our key observation. We can neglect that low order terms. And of course, when we deal with small data sizes, it's not always the case when more superior algorithm in terms of big O would be fast. So classical example, insertion sort. It has quadratic time, but on small data sets, because of that constant factors, because of constant factors, it outperforms Quicksort. So let's have a look. So up to 200 elements, our insertion sort implementation basically outperforms Quicksort. And starting from that, it's comparable. And then with increasing of number of elements, that gaps and grows. So that fact is used in many libraries when combination of insertions on small input data size is used, and for the rest, Quicksort is used. So on the previous examples, we'll see that we have some. So we have that different functions. So we have that linear time, we have sub linear time and log-n, we have quadratic time. So actually, this can be used to classify algorithms. We can say that, for example, logarithmic time is slower than constant time, and linear time is slower than logarithmic time. And that could be true when the size of the input data grows. So the more size of the input, the more that is true. So that's the way, like, to classify algorithms and to reason about them and talk about them. So we can say, okay, we have that we have logarithmic times here, which is better than linear. Okay, let's stick with this. And yeah, we like come into conclusion that why understanding underlying data structures, their performance characteristics, so different implementations, which basically a data structure or some kind of combination of data structure and relationships between these implementations are important. So we have that knowledge, we have that concepts. Now we can navigate the whole library and make a sound decision. It's not obvious. Yeah. First of all, we need to have that understanding. It's not always obvious, but that's the toolbox. Nevertheless, we can like outline the general methodology. We could infer that general methodology that we talked about. So we talked about the concepts. We talked about requirements. We start with the requirements. We see on data. If we understand data, if we understand what kind of operations do we need, then we understand what kind of abstract data type do we need. So it reduces our scope further. Then having like understanding of what kind of abstract data type do we need. We have that list like structure, or we need map here, or do we need set here, or do we need some kind of tree here? Having that, we can pick some abstract type on the most specific level that we need in the Scala collection hierarchy. It reduces so our set of collections more. Then we see that a number of suitable implementations. And as we saw, for that combination of abstract data types and data structures, we have a few options. We could have a few options in the Scala library. And then to make the final decision, we just need to understand which is the best. And understanding the data structure behind that collections is very helpful. So in the end, we came to the concrete implementation. So basically, that's it that I wanted like to show you, and we can proceed with questions, and if we have some.
Yes, thank you, Sergii. Thank you so much for the presentation. And yeah, we have 3 questions. And yeah, the first one from Maya. Could you provide examples of scenarios where choosing the right collection type significantly impacts performance or readability of Scala code?
Yeah, I could provide some example that I had in practice. I worked on the algorithm of like geometry simplification, which is based on so well-known binary heap data structure. So it's very essential for the algorithm to have that data structure, which provides logarithmic time of getting the element from that binary heap, and as well as updating the data. The problem, and there is the reason for that in Scala, that priority queue implementation that we have in Scala doesn't have that update. Yeah, it's very fast to get the element from the priority queue. It's very fast, so logarithmic time to add the element, but it's not fast to update the element. So having that, I thought, so what can I do? What alternatives do we have that behaves in the same way, have similar performance characteristics? How could I replace that to achieve my goal? So I found that so tree-set could be used. So basically, it provides that logarithmic time of even better. So it provides like constant time to get in the head, but yeah, it as well provides logarithmic time to remove and add the element. And by the way, priority queue also provides that constant time of getting ahead. So it has that remove operation, and it was possible just to like replace that update operation with removing the old element and adding the new element. And removing the element in priority queue is not possible. So basically, I understood that the tree set is basically a red-black tree it's not so fast. But anyways, I had no choice. And so just had that knowledge and applied it.
Okay, thank you. And the next question's from Dimitar. Hey, for developers new to Scala, what advice would you give on mastering Scala Collections Library efficiently?
So the thing that we do today, we are trying to understand concepts. So as you saw, there are some concepts behind that library. So there are abstract data types, there are data structures, that abstract things, that are language agnostic, basically. So they're not specific to Scala. They're not specific to any language. They're specific to computer science. So having that, you can understand any collection library. And the Scala Collection Library is not the exception. So Scala Collection Library just has that specifics. It has that some specific things like mutable, immutable collections, and it have that some specific hierarchy that our designers of Scala Collection decided to do that in that way. They decided that that hierarchy would be the most suitable for the tasks. So any task in the world. So decided that in that way. And knowledge of that concept just helps you to navigate through that hierarchy. It helps you to understand why we have that hierarchy. Why do we have that kind of implementations, and pick the right one. So, and in that way, you just learn it. So you have that concepts in mind, you like practice, and you learn. And of course, you have that documentations, which are pretty good, I think, and on the Scala language site.
Okay, great. Thank you. And the last one from Anka. In your opinion, what are the most common pitfalls or mistakes developers make when selecting Scala collection types, and how can they be avoided?
I think the most typical example, when you try to use a specific collection type in your interface code. Yeah. So I mean, we have that notion of interfaces, like signatures of functions or like traits, and we have implementations inside them. And I sometimes I see that people use, for example, list. Yeah, list everywhere. So it's not good because list is not the most fast data structure in many cases, and it's not good from the many points of view. It's not that code is not flexible, and so what if you decide to change your change your code? So it's like one of typical errors that I saw, to use that specific implementations in interfaces. So just pick the most, that the most suitable abstract thing for your code. So if you think that your code should work with sequence, yeah, just pick sequence. If you think that your code should definitely have that indexed sequence, pick that. So another thing that I think not always correct. People just use default implementations. So they take that, for example, sequence, and they expect that the Scala library provide the most, like, so they don't care. So I think in some situations it's okay. We need to understand just if you write some, like, I don't know, experimenting or trying to write some code snippet, it's okay. But if you write production codes, it's not always okay, because default implementation of sequence is just a list. As we saw before, even in the simple linear search, list is not fast. Just, for example, array based. So if you have that linear search scenario on the data that just don't changed, they are more suitable array sequence implementation. So it contains array behind it. You put the data once in it and you search the data in the array many times. It would be much faster than the default implementation, for example, which is a list. So basically, I think that the most typical things that I saw in my practice, that those things.
Okay, thank you so much. Thank you, Sergii, for interesting information for our participants. And yeah, see you at the next events at Intellias. Thank you so much.
Thank you.